Welcome once again, Fraser Nation, 6.2 linear and angular velocity. I believe this is an important section, kind of a crossover to some of y'all who might be taking physics. In our purposes, we're just using these as formulas to basically see how fast you're going around a circle. It's an important thing when we're talking about radians. Students will be able to find angular and linear velocity. Basically, in this section, all you're doing, you need to know how to convert revolutions into radians. You need angular velocity and you need linear velocity. It's just some formulas that you're plugging in. Remember, pi is used for radian measures, so you're not going to see degrees. And if you see degrees, you need to be able to convert back into radian mode. Theta means unknown angle. In this section, it means angular displacement, but it will still use radians. A revolution around a circle is 360 degrees. However, we're talking about radians, so don't think 360 degrees, okay? We need to think of 2 pi, okay? And S is used for arc length. So remember the S equals R theta. When we want to know arc length, or like the piece of the circle, we need to use S. Okay. Next, angular displacement. That's the angle of rotation around the edge of a circle. So if we have an angle, okay, so here's standard position, and this is our start right here. Okay, angular displacement is this angle right here, theta, and this is a little too thick. All right, theta. Okay, so angular displacement. So how wide does this angle open basically along the edge of the circle? Okay, so our dot where it starts at is going to follow that angle until it stops. Okay. We will be using radians. Okay. So, I want you guys to remember that. Angular velocity is the ratio, and remember I told you, ratio is a fraction always. The fraction of the change of central angle, here we go, over the time required for the change. Okay, so how wide do we open? Divided by the time it took. Linear velocity is an object moving at constant speed without changing direction. So how fast are we going with respect to the radius? Next, we need our two formulas that we were talking about. So angular velocity. I mean, you can write this stuff down, but this is really the important thing that you want to know. This is omega. Okay, so I want you guys to remember that this is omega. Okay, a lowercase omega. Not W, omega. Omega is equal to theta over t. Remember, theta is going to be your central angle, your angular displacement. You're going to be given your angular displacement in revolutions, and you need to change that to radians. But anyway, here's the formula right here. You need to know what theta is, and you need to know what time is. Linear velocity, same thing. I don't know if you guys noticed this or not, but let's see. Velocity is equal to R times theta over t. What did we say theta over t was in the first place? We said that theta over t is omega. Okay? So, being that we have this already established as omega, we can write this, okay, as V equals R times omega. Okay? That comes up in your homework, so I just wanted to point that out. And let's do some examples. So, example 1, determine angular displacements in radians, round to the nearest tenth. I've been saying, you can use the big decimal if you're not comfortable with plugging in pi and, using the the parentheses and all that. So I'm going to do example 1 2 ways, and then example 2 I'm just going to leave to your own devices. 5.8 revolutions. Changing the revolution, remember, one revolution, so let's say 1 rev, is equal to 360 degrees, okay? But we can't use degrees. So remember I told you it's equal to 2 pi. So every revolution is 2 pi. So we're going to take this 5.8, okay, and we're going to multiply by 2 pi, okay, which would give us 11.6 pi, okay. And if you plug this in the calculator, number one, you can either say, well, no, you just plug that in the calculator, and you would say 36.4 radians, okay. I'm gonna use that decimal example in another problem, but example 2, 710 revolutions, again, same concept. It's gonna be 710 multiplied by 2 pi for every revolution, so a 710 revolution, and this is gonna be 1420 pi. If you're comfortable with your calculator, you really could just type in 710 parentheses 2 pi close parentheses, and both of these answers are going to give you 4,461.1 radians. Okay. Questions? All right. Next. Determine angular velocity round to the nearest tenth. In your flashcards, you need to kind of start to remember that omega is your angular velocity, and your angular velocity is theta over t. Okay, so over here, I'm going to say omega is equal to angular displacement over time. Now remember, we cannot use revolutions here. This has to be in radians. So the first step that you do, and let's put an ST1. Step 1 is to convert this into rad. So we would need to do 3.2 times 2 pi. Okay, because we need radians here. And that's going to give us, and I mean, you don't have to do this. I'm just doing this kind of as a mathematician, simplifying things. 6.4 pi. Now, we can either use this or you can use the decimal, and I don't have the decimal written out here, so give me 1 second. 6.4. So you can either use this or you can use the decimal 20.1061929. You know, you have to use enough decimal places to get your answer as close as it can be. Remember, pi is programmed into the calculator, you know, like hundreds of decimals. So don't round until the end of a problem. So we can either do 6.4 pi over 7, because t is time, so 7 seconds, or we can do 20.1061929 divided by 7. And when you plug this in, either way, like in the calculator, you're going to get 2.9. Okay. I'm not going to really worry about the units, just as long as you're applying your formula right. Same thing for example 4. We have 700. Okay. So let's call this step 1. And I should have said step 2 right here. Your fault. Okay, so step 1, 700 times 2 pi, which is going to be 1400 pi. Or, you know, you can use the big decimal if you're not comfortable using pi by itself. And this is going to be 4398.2297150. Okay, and then step 2, it would be 1400 pi divided by 15, or you can use either one. 4,398.2297150 over 15. And it doesn't matter which one. I'm gonna start doing this one from now on. You can go ahead and call it 293.2. Okay. Angular velocity. Let's look at linear velocity. I think it's a little bit easier to use linear velocity. Let's remember that linear velocity is v equals r and then theta over t. But remember, we already know what theta over t is. And oh dear, I don't know why these say w. We have to change these. So let's change this real quick. Let's see. So we need omega and we need omega. Okay, I apologize for that. That was kind of weird. All right. So anyway, remember that theta. So let's say remember omega is equal to theta over t. Put that theta in there. Okay, so I have omega right here, and so it's going to be v equals r, which is 12, okay, r, and then theta over t, so 36. Plug these two in, and you're going to get 432. Okay, that's your linear velocity. It would be, I think it's feet over inches, something like that. I'm not worried about my units. Okay, not for now. Example 6, V is equal to, and wow, this is not supposed to be 5p, it's 5 pi. Must be a font change. So this is going to be 5 pi, and actually, nope. This is going to be 7 times 5 pi, okay? So you could get 35 pi, and when we round to the nearest tenth, we're going to get 109.96 or something like that. So it's going to be 110. Okay? Questions? This is the end of the video unless you want an optional word problem. So let's look at that word problem. This is optional. Really all y'all needed was what I gave you before. But a geosynchronous equatorial orbiting satellite, a geosatellite, orbits 22,300 miles above the equator of the Earth. It completes one full revolution every 24 hours, and we're going to assume that Earth's radius is 3,960 miles. So how far will the geosatellite travel in one day? So let's get a good old circle going here, and let's call this Earth, okay? So for A, let's call this Earth, okay? And we said that from radius, that's going to be 3,960 miles, okay? But you have to remember also that we are 22,300 miles above the Earth, okay? So there's a bigger circle to be concerned about here. Let's see if we can actually make this circle right here. All right. Nah, I'm not gonna try that. Let me not try that. But anyway, if you can picture this in your notes, there's a bigger circle to be concerned about. Okay, and I'm not gonna go all the way around, but there's a circle that goes around with radius. You got to add these two together. So for A, okay, your radius of that big circle is 3,960 plus 22,300. And your radius here is going to be 26,260 miles. Okay. And how far will the GEO satellite travel per day? That's arc length. Okay. How far is it going to go around your circle? So that's S equals R theta. So since this is S equals R theta, and we know what R is, and we only do one full revolution. Remember I told you, revolution is 2 pi. So this is 26,260 times 2 pi, okay? And your final answer would be 164,996.4 miles, okay? So that satellite is going around the Earth, or above the Earth, 164,996.4 miles, okay, every day. B is, what is the linear velocity? Okay, so the linear velocity, remember, is V equals R theta over T. Okay, try to get that theta going here. And so we know what the R is 26,260. And then we're going to multiply by 2 pi, okay, because we're only doing one full revolution, over 24 hours. Okay, that would be your time. And you plug this in your calculator, and you're going to get 6,874 miles per hour. Okay? So, remember, word problems are starting to give them the assessment. So, even though it's optional, you might want to write this puppy down. I'm going to review for a quiz that you guys might want to review with. So, hey, see you later.